What actually controls how fast a neural network learns, not the data, not the architecture, but a single number called the learning rate. Let's build a real intuition for it from the ground up. Imagine you're standing on a mountain in thick fog trying to reach the lowest point in the valley. You can't see the bottom, you can only feel which way the ground slopes under your feet, so you take a step downhill, feel the slope again, and step again. The only real choice you have is how big each step should be. Too small and it takes forever. Too large and you go flying across the valley, overshooting the bottom again and again. That step size has a name. In a neural network, it's called the learning rate. Training a neural network is exactly this walk downhill. The network has a set of weights and a loss that measures how wrong its predictions are. Learning means rolling those weights downhill on the lost surface until the error stops shrinking. Every step moves the weight against the slope, and how far it moves is set by the learning rate. Before we touch the learning rate, let's be precise about the problem. A neural network is really just three things in a loop. It has weights, the numbers it can adjust, it makes predictions from those weights, and it has a loss, a single number that says how bad those predictions are. The entire goal of training is to find the weights that make the loss as small as possible. So how does the network know which way is downhill? Through backpropagation. In the forward pass, the input flows through the network to produce a prediction, and the prediction is compared to the truth to get the loss. Then in the backward pass, that error flows backwards through the network, and using the chain rule, it computes a gradient for every weight. The gradient answers one question: if I nudge this weight, does the loss go up or down, and how steeply? That's the direction. The learning rate is the distance. It's worth pausing on what that gradient really is. For a single weight, the gradient is just the slope of the loss curve at the point where you're standing. If the slope is positive, meaning the loss rises as the weight grows, the gradient is positive and the update rule moves the weight to the left, decreasing it. If the slope is negative, the gradient is negative and the weight moves right. Either way, subtracting the gradient always walks you downhill. And notice something elegant: the steeper the slope, the larger the gradient, so the larger the step. As you approach the bottom, the slope flattens, the gradient shrinks toward zero, and the steps naturally get smaller. The model eases itself into the minimum. Now the single most important equation in training: the new weight equals the old weight minus the learning rate times the gradient. The gradient gives the direction that lowers the loss. The minus sign walks us downhill. And the learning rate, this Greek letter eta, sets the size of the step. That one symbol is the whole story. Let's make it concrete. Say a weight sits at 5 and the gradient there is 2. With a learning rate of 0.1, the step is just 0.2, so the weight inches to 4.8, a careful move. Turn the rate up to 1 and the step is 2, the weight jumps to 3. Crank it to 10 and the step is 20, the weight overshoots all the way to minus 15, flying past the bottom. Same gradient, only the rate changed. Here's the same idea on the loss curve, training the same model 3 times. Too small and the ball barely crawls, it inches toward the minimum and runs out of road before it arrives, wasting compute. Just right and it glides smoothly down and settles at the bottom. Too large and it overshoots completely, bouncing wall to wall, and if it's large enough, the loss blows up instead of going down. So the learning rate lives on a knife's edge between two failure modes. Too small and training crawls, it wastes compute and may never arrive. Too large and it overshoots the minimum, bounces around and can diverge entirely, with the loss exploding toward infinity. The art is finding the sweet spot in between, large enough to learn fast, small enough to stay stable. Let's see exactly where this lives in real code. In PyTorch, we'll train the simplest possible model, a single linear layer. We hand the model's parameters to an optimizer, here plain stochastic gradient descent, and look at the optimizer's arguments, LR equals 0.1, that's it. That one keyword argument is the learning rate, the eta from our equation, sitting right there in the code. Training is then just a loop. We make a prediction, compute the loss, and call loss.backward. That's backpropagation, filling in the gradient for every parameter. Then optimizer.step applies the update. Each weight becomes itself minus the learning rate times its gradient. Our equation executed. Finally, 0grad clears the gradient, so the next step starts clean. The learning rate does its entire job inside that one call to step. Now the experiment that makes it click. Take that exact same code and change only the learning rate. With a rate that's too large, the loss jumps around and refuses to settle. It oscillates. With a rate that's just right, the loss falls smoothly and quickly toward zero. And with a rate that's too small, the loss does come down, but painfully slowly. You'd need far more epochs to get anywhere. One line of code, 3 completely different training runs. Stop and appreciate that. The architecture didn't change, the data didn't change, the math didn't change. A single number decided whether the model trained beautifully, trained too slowly to be useful, or fell apart completely. So in practice, how do you actually choose one? You don't solve for it, you search for it. The classic move is to try a few values spaced by powers of 10, 0.1, 0.01, 0.001, and watch the loss curve for each. You want the largest rate that still trains smoothly without blowing up. A handy trick is the learning rate range test. Start absurdly small, ramp the rate up over a few hundred steps, plot the loss, and pick a value just below where the loss starts to climb. And if you have no idea where to begin, the common defaults are a solid bet, around 1e-3 for the atom optimizer, or about 0.1 for plain stochastic gradient descent. So if there's a best rate, why not always use it? Because the best rate isn't fixed. Early on, far from the minimum, you want big steps to cover ground. Later, as you close in, those same big steps overshoot. You want to start large and shrink over time, and that's exactly what a learning rate scheduler does. A schedule lowers the learning rate as training goes on. For example, starting at 0.1 to move quickly, dropping to 0.01 to refine, and then to 0.001 to settle precisely into the minimum. Big steps to get there fast, small steps to land gently. We'll go deep on schedulers in a future video. For now, just know they exist to give you the best of both worlds. Let's bring it together. Backpropagation gives the gradient the direction that lowers the loss. The learning rate sets the size of each step in that direction. Direction from the gradient, distance from the learning rate. Choose it well and training is fast and stable. Choose badly and the model either crawls or explodes. Of every knob on a neural network, the learning rate is usually the first one to tune. Direction from the gradient, distance from the learning rate. That's how a network finds its way downhill. Thanks for watching.